Thank Chair for the introduction, and also thank you, Mira, for the kind invitation. Really great pleasure to be here. So I arrived last night, so pretty much jet lag. So right now it's in China it's like 6 or 7 a.m. So it seems like I just don't have sleep last night. Anyway, so I'll try to keep myself awake and also talk about my work in the last, I guess, 10 years since I'm back to China in 2016. Yeah, exactly 10 years. So basically, my background is more of using ab initio molecular dynamics to simulate, say, surfaces or interfaces, and of course. Really, ab initio molecular dynamics to me is not just a computational tool to study those, say, a very complex chemical system. It's also a perspective in the sense that when we come to very complex chemical system, what kind of angle we would like to take. So, of course, it's too complex. People tend to make assumption before we even do any calculation, or we can take a slower step. We try to take all the factors into account, really slow and expensive. So that was the idea for many years since my PhD. But of course, then this AI acceleration, machine learning potential kicks in, really solve a lot of problems we have in the last 20 years or so. Okay, okay, I gave probably, many of you may already see these slides, just keep it short. So it's all about energy right now, also in Xiamen University, lots of groups are focused on energy problems. So to me, what is really important, all this energy-related process is actually happening on surface or interfaces. So the surface catalysis and interfacial electrochemistry is surely very much important. And also surrounded by experimental groups in Xiamen University, many of them actually are do characterization of those complex systems. So that's also putting me in this environment. On the one hand side, we need to tackle very complex system, but experimentally they try to simplify things, right? Working on, for example, single crystal electrochemistry, and they do spectroscopy, try to measure the structure or the structural dynamics of those systems. So that's all really give me lots of, say, experimental insights, what's happening on those complex systems. Yeah, that's really the fortunate to be there. And also, we know that those are applications. So battery fuel cells, that's all people talk about back in China these days right now. And also, I just want to emphasize that although the society will want to cut the carbon emission, right? But still, the society require chemicals, so the catalysis industry will remain strong, in my opinion. Eventually, we need to. That's what all chemistry is about, right? Making chemicals for the society. So, as I mentioned, that my background is more of the ab initio simulation of the electrochemical interface, for example. The electrochemistry has a really long history, right? Almost 250 years, if you think about. But the ab initio electrochemistry is rather brief. If that precisely indicates that how complicated the system is and how difficult to apply ab initio method to simulate such systems. Okay, when I said ab initio simulation, I really meant for this ab initio molecular dynamics, or also known as the Carl-Parnello molecular dynamics. That was the photo I taken in 2019. Julia was also the chair for this interview with Roberto and Michela. So Michela was talking about the development of the ab initio molecular dynamics. He basically gave like three features. One, there's no fitting parameters, which means it's accurate and has predictive power. And you can use the method to calculate properties that depend on electrons, like IR, Raman, NMR, and so on. And most important, that's really quite enlightening moment for, at least for me. Ab initio molecular dynamics was meant to simulate or to understand complex chemistry. Okay, so if you think that's really combine electronic structure theory and molecular dynamics to tackle those complex chemical systems, where we really have to take into account both the quantum and statistical mechanical effect at the same time. So in the following, I will quickly give you two examples from my own research, which we believe ab initio molecular dynamics is really key in understanding those systems. So electric Doppler, that's in the morning, we already, Michael gave a very good introduction already on this model, and the recent development is really stunning. But just to point out that this Gui-Chapman-Stern model has been existing for 100 years, right? The experimental still use this model as a really primary concept model to think about the electrochemical processes. So the model consists of two parts, this compact Helmholtz layer and this Gui-Chapman-Stern, Gui-Chapman diffuse layer. So this model accurately predicts this so-called Gui-Chapman minimum dilute limit. So for ab initio molecular dynamics simulation, we want to focus on this compact Helmholtz Doppler. So that, just to point out that in the traditional model, the Helmholtz Doppler is really treated as a two-plate capacitor, where the capacitance is constant against potential, but it's really not the case. From experiment, you can really show lots of metals show this so-called bell-shaped Helmholtz capacitance. This you really have a maximum near the potential zero charge, actually slightly more positive with respect to the potential zero charge. Platinum, silver, all the same. In the field, that's already proposed quite many years ago by, or noticed by Trussati and also Schmickler. I think this is related to the electronic structure of the metal electrode. So something, and they apply this Jellian model to explain this, right? So in the Jellian model, you have electron spill over in vacuum, so that will create this surface dipole. And in contact with electrolyte solution, that will give you sort of like pushback effect. The electron will transfer back to the electrode. So that will introduce, that will have a dielectric response, right? And through this derivation, Schmickler proposes a negative capacitance behavior. But just to point out that Jellian model is normally good for SP metal. So many of the transition metals are good electrocatalysts, like platinum, right? We also think of, so catalysis, you think of chemisorption, where you have species or reactants, chemisorption on the surface, that are all interacting with the rather localized D band, right? So that's certainly important to understand this effect. So we set up ab initio molecular dynamic model on platinum. So just quickly show the result here. It's like, so that's a really standard trick we use. Is a neutral interface. We put the counter ion in this solution. In this case, is that must be fluorine, or yeah. Then the positive charge will goes to the platinum surface. Then the ion will take that's a anion, right? So that's the electronic ground state. You have a natural electron separation. But anyway, they will build up this compact Doppler in our ab initio molecular dynamic model. So you can see here a positive charge surface. You have many water chemisorphed with oxygen really touch on the platinum. And if you shift the potential to negative, the same model, really the same trick. You can see the water start to have a proton point to the surface. So it wouldn't surprising, right? So at the very negative potential, the partially positive charged proton will facing the platinum surface. But the thing is, if you look this peak, right, that's the oxygen density as a function, as a distance from the surface. So you can see this peak really changing as function of surface charge density or the potential. At the very positive potential, you have large peak, sort of this water with oxygen chemisorphed on the platinum, right? So that's really the water p electron interacting with the d orbital on the platinum. And when the potential goes to negative, the peak sort of diminish. Eventually, all the proton will point down and the oxygen leave up. So you can see there's a water chemisorption, desorption dynamics when varying the potential. When I said water chemisorption, so you would imagine there will be a charge redistribution due to this chemisorption effect. So that turns out it will lead to dielectric response. That's a charging capacitance, the charging curve we calculate the surface charge density as function of the potential, and also that's the coverage of chemisorpted water. You can also see this S-shaped sigmoid curve. So there's a very negative potential, or the proton point down, you have no chemisorpted water, and around potential zero charge, you have roughly 0.2 mononaire chemisorpted, and it will eventually saturate around half mononaire at a very positive potential. Then that if we take derivative of this charging curve, we get this differential capacitance, this bell shape that exactly reproduce what experimentally see in here. So that could be understand, this Helmholtz capacitance can be understood by, again, separating the effect from the normal water orientation, rather standard one, and also the chemisorption. This Franken type adsorption isotherm can actually give you a negative capacitance. So those two connected in series will reproduce this bell-shaped Helmholtz capacitance. So maybe just one more word, why this peak is slightly more positive than the potential zero charge is just because the maximum of this curve comes with the middle of this adsorption isotherm, right, from zero to half mononaire. So the middle point is actually around 0.25 or so, but at potential zero charge, this adsorption is around 0.2. So that gives this slightly more positive than the potential.
Jun, question. So what do you have adsorbed over this whole potential range between minus 0.5 and plus 0.5? Is it all about water molecules, or?
It's a chemisorpted water. Okay. The chemisorpted water are referring to first peak, right, where you have the oxygen point down, direct connect to the platinum.
But then at minus 0.5, you already are in the hydrogen chemisorption region.
Yeah, that's actually a good point. Is that the same reason I asked you the question in the morning? In this model, we don't have any specific adsorption of hydrogen and OH. So that's exactly for this reason, our differential capacitance curve looks much broader than the experiment. Okay, because experimentally, this potential you got hydrogen UPD, right? And the surface is covered by hydrogen. Okay, so that's another discussion. So right now we're looking for looking into the double layer region, but of course for platinum real case, the double layer region is too narrow to be compared against, right? So. Anyway, the pH effect certainly should be taken into account. Yeah. Okay, just to point out, this negative capacitance to me It's really, if you think about this physical origin of the negative capacitance, it's due to the electronic response, okay? Due to adsorption dynamics, the interface water. Think of the community, there are two groups of thinking, right? One is we want to treat the electrostatics of the electrodouble layer. Many people in the field apply a classical molecular dynamics where you don't treat electron structure. Even you have polarizable force field for the electrode, still missing the chemisorption part. And of course, for the DFT community, where we want to look at the electrocatalysis, for instance, where we do not explicitly treat the molecular dynamics of the electrolyte solution, you will miss out this effect. So ab initio molecular dynamics is really key in treating this system. Another example, just quickly, so it's the same for oxide. In this case, that's tin oxide, where the surface charge is not due to the electronic charge, but due to the proton charge. So then the charging of the oxide is due to the acid-base chemistry. You have proton exchange with the solution at a certain pH, right? You can get charge. And in this case, tin oxide water tend to dissociate at least half, depending on the surface charge density. At the point of zero charge condition, you have around half mononaire water, chemisorption water dissociate. But if you change the surface charge density, you can see this fractional or this degree of water dissociation also change. So it's sort of the water dissociate or not. Okay, they have different interface dipole. Okay, water, molecular water, or dissociated water. So if you have charged surface build up field at the interface, they will change the water dissociation. Okay.
And may I ask a question? How do you define the surface charge density in your calculations?
Yeah. Again, we do really simple trick, right? We just add certain number of proton on the surface and put the counter ion. So that's the thing. We do like fixed number of particle. It's not like ground canonical thing, right? Particularly when you talk about pH, that's basically constant chemical potential for the proton. For the moment, and if you think about it, all the DFT community right now, we are doing for electrocatalysis, we do titration, right? It's like you calculate the surface phase diagram. We don't explicitly require the system to equilibrate between the surface species or interface species. It's me. The time scale is normally not enough to equilibrate that. So we don't have the equilibrium between the surface proton and the proton in the solution.
Yeah, but you see, my point always is that if I was to calculate the surface charge density by a charge scheme,
yeah.
Which volume do I integrate over to define my surface charge? I mean, where does the surface end?
The proton is just on the surface.
Yeah, you just take the proton, but if you take also the electrons, where is it? You see, if you take the whole double layer, it's always zero.
Yeah, okay, we can define, first of all, it's non-electronic charge. It's a proton charge, okay? You don't have like an electron conducting in this case. It's a tin oxide. It's a semiconductor. And also the proton, the identity of the proton, you can basically define by inspection, almost like, right? Yeah. Anyway, just to point out that when you change the surface charge condition or the potential, if you like, the water structure, again, change. In this case, it's due to the acid-base chemistry. The water dissociate. The degrees of water dissociation changes. That, again, give you a dielectric response due to the different interfacial potential induced by the molecular water and the dissociated water. That will, again, give you this bell-shaped differential capacitance. Again, that's even more complex because the contour ion, that's also Annabella also show in her work that the ion can form so-called inner or outer sphere complex. Then they will have located at different position from the surface. Surely will give you different capacitance. Okay, just to quickly show, to understand the, let's say the dielectric behavior of the double layer metal and oxide is very important, taking into account both the electronic structure and also the molecular dynamics. Another example I quickly show is really my PhDs. I do surface catalysis very well, like Axel working on this for many years. Is a surface science approach. Experimentally, in order to really see the absorbate at high precision, you need to do that at the ultra high vacuum condition and at very low temperature. And the same, the DFT calculation is a really good correspondence, right? We do the optimization, we locate the most stable structure at 0 Kelvin, and then we can even locate, search for the transition state. That's all nice, very good correspondence between theory and experiment. But in the community, soon realize there's a huge gap between the conventional surface science approach and the real-world heterogeneous catalysis. Is that because there's a huge gap, right, in both the environment, pressure or temperature gap, and also the materials gap. Very open, we are looking at very complex nanostructures, right, instead of the single crystal surface. And the development of the in situ characterization also show that the surface undergoes huge change under reaction conditions, like a gold nanocluster from the TEM. You can see the structure change a lot. If everything's moved, right, we better not to think, have like a simplified picture we show for the undergraduate student, in the chemistry student in the textbook. It's like for the potential surface, we have very well-defined minima for the reactant product and also for the transition state. But rather, the structure, the potential energy surface will look like this. Eventually, you need to sample all the possible configurations associated with the different states, right? So we have to really calculate the free energy. So an early example we do is the oxygen dissociation on gold 13 cluster, very small cluster, but just applying ab initio molecular dynamics and enhanced sampling technique, we can calculate the free energy profile for this reaction. So, and when we do molecular dynamics, of course, we will have temperature, okay, which is missing in the standard DFT calculation. So we calculate the free energy profile. That's the free energy profile at different temperature. Just to show in here, so that's a red curve is the free energy change as a function of the temperature. And the blue curve is actually the free energy barrier. The trends are similar. Let's just focus on the red one. Just showing here this dashed line is actually the standard geometry optimization approach. Then we add on vibrational entropy for corrections. You don't see any structure, the temperature dependence, right? Low flat. But if we do free energy calculation, we see a sudden jump at the intermediate temperature range. Again, take the temperature derivative of the free energy, you get the entropy. So that's the reaction entropy as a function of temperature. You see a huge peak here. So that's a non-trivial entropic effect. And even more interesting, why? Just to show you the magnitude. When we first look at this curve, check the magnitude, right? It's 2,000. So that doesn't really look promising, because for quite a while we thought we did something wrong. But anyway, we did a lot of analysis. Eventually, we found out that along the reaction pathway, for the different states, they actually have different melting temperature. If you think about such a high entropy change, it could only led by phase transition. Okay, let me just quickly explain here. So that's the heat capacity curve. We calculate the total energy as a function of temperature. So you see at some point as a jump, that's due to a solid to liquid phase transition. And interestingly, for different states, reactant and product, so reactant will be one oxygen molecule absorbed on the gold cluster. The product will be dissociated product, two oxygen atom absorbed on the gold cluster. The transition temperature are actually different. Just using this, I will quickly explain why we have this huge peak in the reaction entropy. So at the low temperature, both reactant and product actually are more solid state-like. They have very low entropy, but their reaction entropy, delta S, is very small. At a high temperature, both states will eventually melt. Both states have liquid-like state. They have high entropy, but their difference, again, is small. What is interesting is in this intermediate temperature range, the reactant in here is still solid state-like, but the product start to melt because you have a mismatch in the melting temperature between the two states. Then the reaction entropy will start to increase because the product start to melt. And when you increase the temperature and the reactant start to melt, then the reaction entropy, delta S, also just goes down. Just following this range, it's like at this temperature range, the reactant, when we have an oxygen molecule absorbed on top, is a solid, including the cluster. Along the reaction path, when the oxygen molecule, the two oxygen atom, you're pulling apart, the whole cluster start to melt. Okay, that will lead to an entropy increase and then a free energy decrease. So that to me is this anomalous increase in the reaction entropy due to the phase transition is a new type of catalytic effect. Only after we using ab initio molecular dynamics do the free energy, the full free energy calculation, we could capture this, right? The standard DFT approach neglects all the temperature effect and the entropic effect. So just again, just an example, we believe ab initio molecular dynamics is really key to understand the fully understand the dynamic catalysis, right? Okay, just two examples on ab initio molecular dynamics to start surface catalysis and interfacial electrochemistry. They are really important. It's just way too expensive, right? As we all familiar with, right? But in the last 2 decades also, the field now is really revolutionized by the development of machine learning potential, right? So I don't have to explain too much on this, but just to point out that we using the potential collaborating with Roberto and also Weinan and also Lin Feng. Also, equally important is this active learning or concurrent learning workflow to generate the data set so that we can accurately reproduce the DFT data that is important. With the acceleration by AI right now, we start to move away from just simple ideal model system to much more complex and realistic system. So that's, of course, what my experimental colleagues always push me to do. So finally, we have some solution for that. As I said, the data set is really important, and especially if we want to calculate the free energy, also the free energy barrier, we need to combine the active learning with the enhanced sampling, right? So that we can also cover the transition state region, so that we can automate this training of machine learning potential and also calculating the property, physical property, and redox potential, those type of free energy with this square kit workflow we're developing. I meant to remove this, but anyway, just quickly describe. Now we can train sort of like more of a universal, but it's not a universal. People now do periodical table. We try to just focus on this domain problem we want to address. Like in this case, this battery electrolyte, we can develop a rather universal machine learning potential for battery electrolyte for calculating, not just simulate the structure, but the property, right? Like the redox potential and so on. One more point on that is also Julia said in the morning as well, and spectroscopy to me is also important. That's this when we study very complex structures. How can we be sure our simulation model is really relevant or representative of all realistic system, given the functional may have problem, our statistical error may not be factoring, right? So spectroscopy is really important. And we can also, for this concentrated electrolyte, we can not just calculate the solvation structure, but calculate the chemical shift, right? That we can even compare with the experiment. In this case, when you change the concentration, the chemical shift really shows a turning point. That's reflecting the really complex change in the solvation structure because they are really complex. But experimentally, indeed, reproduce this turning point. That sort of show the structure must be sufficiently representative. So that's similar things about the vibrational spectra. So the surface enhanced Raman spectroscopy is one of the key area in Xiamen University. So now we can calculate those Raman spectra in direct comparison with the experimental work on the same system. So they do on single crystal, right? So we can start to look at this. Okay, now back to the catalysis. So using the ab initio molecular net, we show for this very, very small system, this phase transition catalysis. But you wouldn't think of, because in catalysis, normally we have nanocluster, right? You wouldn't think of a small fraction of change of the state of the surface absorbed would change the whole phase behavior of the nanoparticle, right? But what we show in the following is we can now train a machine learning potential to simulate a much larger cluster, a nanocluster. And it turns out we don't need the whole cluster to melt, right? Only the surface one or two layer of the metal melt will lead to this phase transition catalysis behavior. The model system is CO2 dissociation on copper 55, so it's a 1.5 nanometer. You can see there are two jumps, okay, in the free energy profile, similar to what we calculated, but two jumps. So it turns out the first jump is actually due to the surface melting, and then the second jump actually due to the core melting. So you can really see the change of the absorbed state can already change the phase behavior of the surface layer of the metal nanoparticle, can directly contribute to the catalytic effect. And we also look at the point defect in this case, because nanocluster tend to have many, for example, vacancy or other atom. With vacancy, we can see the surface melting temperature decrease by roughly 50 or 100 K. But what, to our surprise, if we have one other atom, this point defect, they can reduce the surface melting temperature by almost 200 or 300 K. So that's just because this other atom can penetrate inside the surface, will cause strain, and then make the surface more dynamic. Okay, just to quickly show, and this melting temperature is around 300 K. It's literally room temperature. Okay, so you would imagine the surface of nanocluster catalyst is more dynamic than we would expect. Okay, with this, I guess that's really just to point out, that sampling require like 2 billion configurations in order to calculate the free energy and the free energy temperature dependence of the free energy. So without machine learning potential, it wouldn't be possible. But it poses a conceptual problem to think about now. We used to think of structure-activity relation in catalysis. That's all sort of rather rigid, fixed configuration. But now the surface is so fluid-like, what kind of structure we are talking about? So this dynamic structure-activity relation will be very useful for the field to think about and move forward, how we utilize or design principle to utilize this dynamic effect. Okay, with this, I will come to my last part. How long? I still have 5 minutes? Okay, okay, that should be okay. So we all know the machine learning potential is good, but it's all previous work all based on this local representation, right? That's also due to the efficiency. I'm sure many people are using this. But for electrochemical system, it's certainly not enough. That's the work that was shown by Annabella. That's a charged TiO2 water interface. And they show if you're using the short range machine learning potential, the deep potential, you even break the charge neutrality in the bulk electrolyte. So that's the distribution of the cation and anion. You have a mismatch in the bulk solution. So that's certainly not enough. So the electrostatics is not well respected by the short range machine learning potential. And with the long range DPLR, they can recover this charge neutrality in the bulk solution. Okay, so long range is certainly important, right? But for now, all the machine learning potential, they all made electron structure, we know that. And we also need to take into account the polarization. That's something well defined for the system, and how the system responds to the applied field will certainly essential for really simulate charged or electrified interface. But before we do this, we need to think of what type of dielectric response we are talking about for the electrochemical interface. In this case, we're talking about metal water interface. Annabella showed TiO2 water interface. TiO2 is more of a semiconducting system. In electrochemistry, very often people think of metal electrode. So again, think of electrolyte is only conductor, but it's electronic insulating, right? So you sort of have this rather local dielectric response. But the metal electrode is an electronic conducting. They will have very long local dielectric response. So the treatment will be different. For electrolyte, like Annabella showed, using this so-called deep Vanier, you can using the Vanier localization, right? You get the Vanier center. You can predict the Vanier center using a neutron network. Then you can treat the polarization by summing up all the Vanier center. But it's not taking into account the long local electron response, not for metal, also not for this aromatic organic molecule where you have delocalized pi bond, right? For electrode in the community, people develop various versions, right? Taking into account the long local charge transfer like the QEQ, this charge equilibrium scheme, and many other variants. But this method tend to overestimate the polarizability for insulating molecules. Okay, so they are actually sort of complementary. So thought about this, then we come up with a hybrid representation of the metal-water interface. For electrolyte, we're using Vanier centroid method. It's not the same as Annabella was doing. But for the electrode, metal electrode, because it's non-local dielectric response, in this version, we're using the Siepmann-Sprigg polarizable electrode method, okay? So to make that, to capture the non-local dielectric response. So then the machine learning potential framework for this electrochemical interface is separate into two parts, right? That like many people do in the field. For the long-range part, long-range electrostatics, we explicitly treat the polarization by combining the Vannier centroid for the electrolyte and the polarizable electrode for the metals. And those electrostatics part is taking out the residual energy, that's the short-range one, using the standard DP framework. Okay, so now we have a hyper representation for the metal-water interface. So that's sort of the training set we have. That's including pure water, electrolyte, and also interfaces with various of surface charge density. Okay, just last slides, just quickly show. With this machine learning we call EC MLP. First of all, when we change the surface charge density and the potential, you can see the first peak. That's due to the chemisorption, the chemisorpted water, the coverage change with the potential. And this reproduce the blue circle, blue dot actually from the machine learning part, and the red triangle is from the AIMD simulation, sort of it fits well. And they will also give you this bell-shaped Helmholtz capacitance, so reproduce the ab initio molecular result. Just to point out that, because that to me is important to capture both electronic structure and the adsorption dynamics, right, by this machine learning potential. Okay, just quickly, we also can calculate the energy profile by applying a perturbing field, a very small field. We can calculate the dielectric profile of the water near the interface, particularly in this region, right? Chemisorpted water is negative, so that's due to the chemisorpted water. So it takes roughly 1 nanosecond to converge. So standard ab initio molecular dynamics wouldn't be able to converge this. So with this, I want to conclude. Hopefully, I convince you ab initio molecular dynamics is important for many important chemical, rather complex chemical system, like the electric double layer, and also obtaining a fuller understanding of surface catalysis, particularly putting the temperature effect. This dynamic catalysis was certainly important by using ab initio molecular dynamics. And also acceleration by machine learning potential, it really opens up new opportunities to modeling lots of dynamic effect at a realistic condition. And it's really what I believe treating environment at equal footing is crucial for electrocatalysis. Eventually, hopefully we can get there at some point. And just to say that, okay, time for AI-squared electrochemistry. Okay, so that's the work. Thank many talented students in the group. Jabo graduated already a while from the group. Now he's independent researcher in Ningbo, who working on this negative capacitance. The phase transition catalysis was first work with Jun Cheng. And also the surface pre-melting work is from Fu Qiang, and also the ECMLP work is from Jia Xin, and also many people in the group. Also, that's Lonely, he was in the group a while ago. Also, thank for the collaborators and the funding agencies. With this, thank you for your kind attention.